Hi, it's Miss Heaton signing in to talk with you about enthalpy and Hess's Law. This is a little bit of review from first semester Unit 2 when we talked about thermochemistry, but now we're going to apply it to chemical reactions now that we know what chemical reactions are. This goes along with your textbook, chapter 10.6 and 10.7. So you can refer to that if you would like more information about anything that we talk about here today. So first thing I want to do is review endothermic versus exothermic. First of all, you remember that endothermic means heat goes into the system. So heat is gained by the reaction, by the reactants. An exothermic reaction would be the opposite. So heat would be lost by the reactants. So heat is given off. Now we're going to be using the word enthalpy to describe the energy or the heat today. And that's just heat energy at constant pressure. That part doesn't matter. All you need to remember is that enthalpy means energy, and it's represented by the symbol delta H. If delta H is positive, you have an endothermic reaction. So endothermic will have a positive value for the heat, and an exothermic reaction will have a negative sign in front of its value for heat. And we're going to put some quantitative numbers with that today. And when you include the heat for a chemical reaction in the chemical equation, you call that a thermochemical equation, right? Because thermo means heat, chemical talks about chemicals, so it's the equation that has heat in there. If heat is a product, it is an exothermic reaction. Think about it. Heat is given off, so heat is produced. An endothermic reaction, on the other hand, will have heat as a reactant because heat has to be added or put in to make the reaction occur. So let's take this as an example. We have two waters breaking down into two hydrogens and oxygen. If we were to write this as a thermochemical equation, we would write 2H2O turns into, so our delta H value is positive. Remember that positive means that it's endothermic, so we'd have to write the heat as a reactant. So we'd write 483.6 kilojoules as one of our reactants. Turns into 2H2 and 1 O2. So that would be an endothermic reaction. So heat is a reactant here. Now, how about this reaction? The opposite process, those products turning into reactants, would be an exothermic reaction because the delta H value is negative. So if we were to write that as a thermochemical equation, we would write 2H2 plus O2 makes 2 H2Os and 483.6 kilojoules per mole. You don't write the per mole part when you write it in the reaction. You just write the kilojoules part because it's a mole ratio. So again, endothermic heat will be on the reactant side. Exothermic heat is on the product side. We're going to be applying that today with an example kind of like this. Let's get a better color. I think this white is kind of hard to see. So let's take that same reaction. We'll take the second one, the exothermic one. So heat is a product. We want to find out how many kilojoules of heat are released when we react 5.3 grams of hydrogen with excess oxygen. Remember, excess means you don't have to worry about it. So what we want to do is figure out how much heat will be released when we react our hydrogen. So this is essentially going to be just like stoichiometry. You're going to start with your 5.3 grams of hydrogen. And remember, our chemical equations are written in terms of moles. So in order to use our ratio of 2 to 438.6 kilojoules for every 2 moles of hydrogen, make that much energy, you have to be in moles. So first thing we want to do is convert our grams into moles, and by now you're a pro at that, right? So we know from the periodic table that 1 mole of hydrogen weighs about 2 grams. So if we multiply that out, that would give us moles of hydrogen. We could stop there, get a number. I think you get like 2.6. But what we really are concerned with is how many kilojoules of heat are released. And so then we could say, well, for every 2 moles of hydrogen, we get 483.6 kilojoules. So we could use that as our mole ratio, 2 moles of hydrogen for every so many kilojoules. So 2 goes here because that's the coefficient, and 483.6 kilojoules goes here because that is the amount of kilojoules. So then you would just multiply across by what's on top and divide by what's on bottom. And it looks like you get 630 kilojoules. Now, let's talk about the sign. Should it be positive or negative? Well, heat is being released, so to denote that in your answer, you either need to write 630 kilojoules released, or even better, write negative 630 kilojoules. I do have the right number of sig figs. Yep, 2 sig figs here, so 2 in our answer. So if it's an exothermic reaction, you either need to write released or include a negative sign before your answer. If it's endothermic, it would be 630 kilojoules absorbed or a positive number of kilojoules. We'll practice that more in class. One other thing we need to talk about with energy, endo and exo, is enthalpy diagrams. These are from your textbooks. You'll see these again when you read. But basically, an endothermic reaction starts with a low energy for your reactants. They react, and they now have more energy. So the amount of energy has increased. It's an endothermic. Exothermic, on the other hand, starts with a lot of energy in its reactants, and it reacts and then gives off energy. So the delta H is the difference in energy between the reactants and the products. The delta H would be positive for endothermic, and it would be negative for exo because it's going from high to low. We're going to look at those diagrams again later on in this unit in a slightly different form. Now, it's possible that a reaction takes more than one step, kind of like if you're doing a chemistry problem. You do the first step, then you do the next step. Same thing goes for reactions. You may do the first step and it's exothermic, and then the next step might be endothermic. And then the overall reaction, you would add those 2 steps together to get the overall amount of energy spent. Maybe an analogy would be like if you're going to open a business, first you have to spend a lot of money to like buy your restaurant and buy your supplies and buy your lemonade and all that stuff, and then you make a little bit of money. And the overall amount that you gain or lose is your overall delta H, or your overall enthalpy. We can use this in something called Hess's Law. Hess's Law is a kind of a law that says you can add up chemical equations or chemical reactions to figure out the overall reaction and find the overall change in energy. And this is useful because you can't always do all the reactions. You can't do it all in one step. So you can look at the steps individually and figure out overall what the energy should be. So for example, let's say we have a reaction where A and B combine to make AB, and then that compound AB could react with D to make a different compound, A and D together, and B by itself. This first step is endothermic. It's positive 100 kilocalories, similar to kilojoules. Remember the calories and joules thing? And then the delta H for the second one is negative 10, so this is exothermic. If you do the first reaction and then the second reaction, what is the overall energy for the total reaction? Well, the overall energy, you could just add those up. You do 100 minus 10, and you get 90 kilocalories as the overall delta H for the reaction. And the overall reaction that occurs, you can actually add these up. And if anything is made in the first reaction and then used up in the second reaction, you can cancel it out. So see how there's an AB that's produced, but then in the next reaction it's used up? That would cancel out. Also, if something is there at the beginning and there at the end, it's not part of the overall reaction, so you can cancel that out as well. So essentially what we're thinking of is all of the reactants as one thing and all the products as another. And if something shows up in both places, reactants and products, it will cancel out. So the overall reaction that occurs is A and D react to make AD. So doing the reaction in one step should give off, or should absorb 90 kilocalories, and doing the reaction in 2 steps also gives off 90 kilocalories overall. You can use this along with some known reactions that have already been studied and already found their delta H values to calculate the energy needed for a reaction that you haven't actually done, to predict how much energy should be given off or absorbed. There's a couple things you can do to manipulate the equations though. The first is that you can flip an equation around. You can make the reactants products and the products reactants. If you do that, you have to change the sign of delta H. So if it's negative, you flip the reaction, it becomes positive. If it's positive, you flip the reaction, it becomes negative. Also, you can multiply a reaction. You can do it 3 times, 2 times, half of a time. And if you multiply a reaction, you have to change all the coefficients by that number. So if you double it, all the coefficients get doubled, and the delta H value gets doubled. That's logical. So let's try an example of that. So here's how Hess's Law works. Usually you're trying to find the overall change in enthalpy for a particular reaction. So your goal is to take these known reactions and manipulate them so that the chemicals add up so that the only reactants are these and the only products are those. So let's look at our reactants and products here. It looks like N2O4 in our reaction here is on the wrong side. See how it's a reactant, but in our overall reaction we want it on the product side? That means that we're going to have to flip this reaction around. We're going to have to do it in the opposite way. So we'll take two NO2s, the products become reactants, and the reactants become our products. So we're basically just doing the reaction backwards. That means that the delta H value is going to be opposite. If the forward reaction is positive, endothermic, the opposite reaction will be exothermic. So we'll cross that out so we remember that we've flipped that reaction around. Then let's see, we need two NOs on our reactant side. Oh, and look, we've got two NOs here. We got an O2 here, O2 here. What about this NO2? Oh, look. Okay, so there's two NO2s here on the reactant side. Those are also produced at the end of the second reaction. So those are going to cancel out. If we started with two, we end with two, it's like they aren't even part of the reaction at all. And if we were to add up these two reactions, we would have two NOs reacting with an oxygen to make a dinitrogen tetroxide. That's the overall reaction that we were going for. Since this reaction now matches our overall reaction, we can add up the delta H values to find the overall enthalpy for this reaction. So you do negative 13.8 plus negative 27, and you should get negative 40.8 kilocalories for this overall reaction. So that was an example of one where we had to flip the reaction. And remember, if you flip the reactants and products, the sign on the delta H gets flipped as well. Okay, let's try one more example. If we were trying to find the overall enthalpy for the reaction where two hydrogen liquids, an H2 liquid, combines with bromine liquid to make two hydrobromic acids that are gases, and we knew these two reactions and their enthalpies, what would be the overall enthalpy? Now, it's important to note that if you're given liquid, liquid, and gas, you probably have to pay attention to that in your reaction. Look at this first reaction. This first reaction is actually just taking liquid bromine and turning it into gaseous bromine. So that's going to be important in our overall reaction here. So let's see. We want to end up with only liquid bromine in our reaction. Liquid bromine is here on the correct side, so that seems to be good. Okay, so H2, we need one H2. We've only got half of an H2 in this reaction. So I think that means we're going to have to double this. So if we double this entire reaction, we're going to double everything. So 2 times 1/2 would be 1, so we'd have just a liquid H2. Half times 2, again, would be 1, so we'd have 1 bromine gas. And that would make 2 times 1, 2 HBRs. And the delta H value would end up getting doubled. So negative 8.7 times 2, that's negative 17.4 kilocalories. So that's exothermic. So we'll cross this out so we know that we have used that and changed it. And if we look at our reaction, will things cancel out that we want? Oh yeah, look, the bromine gas here will cancel out with this bromine gas. And if we add it up, we'd have H2 liquid plus Br2 liquid, making 2 HBr gases. That's the same as our overall reaction that we were shooting for. So that means that if we added up the enthalpy for each of those reactions, we should get the enthalpy for the overall reaction. So 7.3 plus negative 17.4 turns out to be negative 10.1 kilocalories. So that would be an exothermic reaction overall. Okay, folks, that is it for today. Come to class tomorrow and we will be practicing more of these. Some of them will get a little more complicated. Some will be this easy. So review this if you need to out of your book, chapter 10.6, 10.7, and happy reacting, exotherming? I don't know. See ya.